The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Great. Okay, so today's lecture is on transit service reliability. This is my penultimate lecture because we have guest lecturers too. So let's start out with what is reliable transit for you? What do you think of when you think of reliable transit? What does it mean for you? And I'll write a few videos on the board. So
arrival at or close to scheduled arrival.
Okay.
Low variance of
There's a word for that, punctuality, right?
punctuality.
So let's use that. Just because it's hard to write on the board with chalk. It's hard to spell correctly actually when you're close up to the board. Emily.
Lack of disruptions. So, you know,
Okay.
it's the same service every weekday.
And you kind of got two of them. Lack of disruptions is one of them, and you said the same service, right? So I guess predictability. Great.
I like the word legibility, which is that you sort of know where the transit is going and it makes sense.
You call it legibility?
Legibility.
Okay. It's quite a unique term there.
Well, yeah, okay.
You have one.
Oh, not in the U.S.
Let's get that off there. I appreciate the humor though. Any other ideas?
Maybe the quality of the ride is always the same. Like
So
vehicles are clean.
consistent quality.
Yeah. It's always possible to enter the car.
Okay, so
Routing is consistent.
sufficient capacity.
I think it also has to like cover all the places you want to go in like a 90 some kind of percentile of what you want to travel. So you're not like getting the car also or something.
Yep, and so that includes sort of coverage, which is spatial, and also span of service, right? Which is the same thing but temporal. Okay, these are some good ideas.
I have a real.
Sorry?
I said I have a real one now. Consistent fare structure, or.
Okay, that's usually consistent. Are you thinking of a particular example?
Oh, I think of just like when places where the price keeps rising, like often.
Okay. I'll say, I don't know. How do you want to do that?
transfers can sometimes be
Yeah, good communication of fare
Okay.
policy.
Here. Yeah.
So a clear fare policy.
Sure.
Yeah. Yeah, Eli.
I feel like we haven't worked in like maintenance of headways and high frequency service in here.
Sure.
It's
So
kind of covered by punctuality and
right. So, but it's a little different, and we're
Yeah.
going to talk a lot about that today. So let's add that in. So sort of even headways.
But you wouldn't say like short headways. That's not necessarily part of reliability. Right?
well, it seems like we're sort of actually expanding the traditional definition of reliability here. I think it is.
We have been. I'm not filtering too much out because I guess we'll stop here. The point I wanted to make is that I'll come back to this in the lecture. Reliability means a lot of things to different people, right? So, and doing all of these things can be difficult. So we're going to talk about some aspects. We're going to focus more on punctuality, lack of disruptions, predictability. We'll talk about how to make quality consistent. That has to do with even headways. We're not going to talk so much about fair policy or coverage or span of service or legibility. All right. So impacts of unreliability, the causes of unreliability, how to measure unreliability or reliability, and then real-time control strategies. And we've mentioned some of these topics before, and now let's focus on these things. Okay, so passenger impacts. Now, what happens when service is unreliable? We have longer waiting times, right? We have the need to have a longer reliability buffer. So have we talked about reliability buffer before in this course? No? So if your trip to, we're going to talk more about it later, and we'll hear, but if your trip to, okay, so you know that running times are stochastic, right? So there's a distribution of running times. So this is running time, or in this case, let's call it journey time. And this is it's a probability density function, right? So the schedule has to have a single deterministic value, and you can go to your journey planner and it'll say your journey takes this long. You walk this much time, you wait this much time, you arrive at this time. So you add those components up and you have a specific time. That specific time may be maybe close to the median, maybe not. So if service is reliable, then there's little variance in this distribution, correct? So you might have, I don't have much of another color here. No, that doesn't work. So I'll just write on white as well, maybe dashed. So you might have one distribution of journeys that has lower variance, and therefore you need to budget less time to make your trip and arrive on time, correct? So to the extent that the waiting is variable or your in-vehicle time is variable, then if you need to be at work or at school at 9 a.m., that means that even if on average it takes half an hour, you might have to budget for 45 minutes. So the extra 15 minutes of time that you budget, that's called reliability buffer. And it's a cost, right? If you could monetize it if you wanted to. It means that people are budgeting and in some cases wasting that time, and we want to decrease that. So the need for trip time reliability buffer. Higher loads. So that means, of course, that vehicles have more people in them, and therefore rides are more uncomfortable for passengers, and they are also slower, because if a vehicle has more people in it, the bus stops more often, and the dwell process is slower. We know that from earlier lectures. We know from random incidents that from a passenger perspective, passengers will experience more crowded vehicles because they are more likely to board the vehicle where there are more people in it, right? It's a little bit of a chicken and egg problem. So even if on average across the vehicles your loads are right where they should be, most people are going to be on the more crowded vehicles. So that's a bad thing. In terms of agency impacts, can increase cost, making, for example, you need a longer recovery time at the terminal, and therefore you know that translates to higher vehicle costs, higher crew costs, reduced ridership and revenue, reduced operator morale, a public and political problem. What do I mean by that? What happens when public transportation is unreliable in terms of politics? Huh?
Public hates it. Public hates unreliability.
Sure,
And
so
it creates pressure. The forces against public transportation grow stronger.
Sure.
So
So
they provide funding and then
yeah, so there's a funding, right? And we'll talk more about this in the last 2 lectures. So when public transportation is unreliable, sometimes governments are hesitant, or the public may be hesitant to fund it more before they fix the problems, right? But fixing the problems might require some resources. So it's a vicious cycle. And then reduced effective capacity, and we'll show a real example here in Boston of that. Right, so what causes this? We could divide causes into external and internal causes. External causes, traffic, demand variability in particular, incidents, so a passenger might get sick. These things are external. The agency knows that they could happen, but there's not much you can do about them. Internal causes are in the control of the agency, at least a little more. So equipment failure, that's something that the agency owns. Maybe they can't predict exactly when it will happen, but with some preventive maintenance, they could reduce the chance of this happening. Insufficient resources, poor operations planning, lack of supervision and control, and human driver behavior. What do I mean by human driver behavior? How does that cause unreliability? Henry.
The way that a driver drives can vary, and that affect runtime, or maybe some are more aggressive and some are
Yeah,
less aggressive.
some drivers are slow, some drivers are fast, and then if you're running high frequency service, they'll bunch up, and that could be the cause of bunching. Or maybe that fast driver is now sort of running early, running a long headway service early, and that's really bad for waiting time, as we'll see. Okay, so if we think about transit and look at the whole process of sort of planning it and delivering it as if it were a business process, we know that we start with service planning and move on to operations planning and then actual operations. And that each of these things, sort of the output of one is the input to the next process and so forth. The input to service policy among them is demand estimation. Then we bring in sort of analysis of models for vehicle scheduling and crew scheduling. And during operations, there's service control. We'll talk about service control, real-time control, as an input to operations to make them more reliable. So there's also a feedback loop, right? Because passengers might complain, or somehow you have data collecting information on performance, and you can take that back to service planning or operations planning, or you could modify your service control to change the cycle. And here we have the different sort of the key agents in each of these steps, right? So transit agency management, mostly taking care of service policy. Then you have some operations planning staff taking care of operations planning, and then the actual sort of drivers and inspectors out in the field. So I guess one thing to take away from this is that there are many decisions across all of this process that affect reliability, right? And you can't really have reliable service if there's many places where you could cause unreliability. One of them might be your vehicles break down, right? So no matter what you do, if your fleet is old and having difficulty with maintenance, you might have the best service control policies and all the supervision in the world, and you still have unreliable service. So it's a hard problem. Right, so it used to be very hard actually, because, well, to measure reliability, you need to measure the variability in things, right? So you know from data collection that if you want to measure the mean, you can calculate your sample size. Measuring the variance of something requires an even greater data collection effort. So things have gotten a lot easier with technology. And so we know that we have several data collection systems, AVL, AFC, APC. That makes it a lot easier and cheaper to measure reliability. We'll give some examples. Then we have scheduling systems, which make it very easy to make an adjustment in the schedule. If we see that we've not scheduled enough time for this bus, we need to add some recovery time. It's going to increase the fleet size by 1. With a program, a software, such scheduling software, you can do that quickly and react. And the best systems will actually read AVL data in, and you can. You don't even have to manually analyze it. You can sort of use the program to analyze it, and the same program will help you schedule. And then there's improved communications technology, which makes it easy to communicate instructions. Hey, depart a little later from this stop or from this terminal. Don't start running without passengers and start operating in revenue service 3 stops down because we have a long gap. So you may have heard you can't really sort of have control. There's so many ways of saying this, but you can't really sort of do something about something until you measure it, right? So measuring it is important. And we'll talk a little bit about performance, reliability as a performance metric. There are different key performance indicators you could calculate for reliability, and that's the first step. You want to measure it, and you want to be able to track your reliability for particular routes or system-wide, and then be able to, if you change the policy, see what the effect is. So one thing about it is, it's not the only thing that matters. Reliability is important. It would be a mistake not to measure it, because you might have a very productive service, but you might have all of these problems that we identified. On the other hand, if you put too much focus on reliability, then it would come at a cost. If you want to make your schedule very reliable, then you can add a lot of recovery time, right? And you could add many timing points and make the buses hold everywhere. That would slow service down. It would increase journey times. Even if they would be very predictable, they would be very long, and that could deteriorate service. So we make a distinction between reliability in low-frequency service and reliability in high-frequency service. What's the difference? We've talked about the weighting strategies for low and high frequency. We've talked about this several times before. What's the difference between a service that runs every 20 minutes and a service that runs every 5 minutes with regards to your strategy to take that service?
If it's more frequent, you can just walk up.
Okay, so high frequency service is walk-up service.
More random arrival.
Right. The arrivals tend to be random. They don't actually have to be for this thing to be valid, for this distinction to be valid. They just have to be independent of the vehicle arrivals, right? So
Although nowadays with
yes, we'll mention that. So with low frequency service, most people will time their arrival at stops so that they are with the schedule, right? So if vehicles are arriving on schedule and passengers are arriving on schedule, people wait very little time. And if there's very little variability in that, if service is incredibly punctual, people would show up the minute before and wait almost nothing, right? If there's some variability, then people have to add some reliability buffer time, right? So even though it says it's going to come at 3:53, you might have to get there at 3:50. Okay, so you then can set, because you want to measure reliability, and people, especially in the US, we call that OnTime Performance, which is a long way of saying punctuality. You could have different threshold windows. And we've talked about performance measurement before. We're just here sort of going back to specifically reliability. One way would be to say any bus that departs the stop between 1 minute early and 5 minutes late is on time. And any bus outside of that window is not on time. And then you say, I am 90% reliable. This bus leaves that stop 90% of the time within that window. And then you could have tighter windows. You could say not early and up to 3 minutes late, or not early and up to 1 minute late. Of course, what happens? Well, let's start with the first one. What's wrong with the first one? What's different about the first one? You allow early departures. What's bad about early departures when you have a long headway service?
people aren't expecting it, they use their bus.
Right, so if people are really timing their arrivals at stops according to the schedule, and it's 20-minute headway service, the bus leaves early. You arrived a minute early, now you have to wait 20 minutes. It's really bad, really bad. This thing is a little, real-time apps help with this, but not everyone has one, and if service tends to be reliable and every now and then it isn't, then people might still have, they're trying to show up to work on time, right? So there's not much the app can do unless there's a good warning ahead of time, this bus is going to come early, you better be there. So you have to rush to get ready. Okay, what happens when you move, so it's good to not allow early departures. what happens when you move to tighter bounds on the late side? Two things happen, right?
Harder to meet it.
So it's harder to meet, and that means that your reported reliability comes down. So you can imagine internally a pressure in the agency to have a little more slack, right, to say that you have higher reliability. What happens in terms of performance or in terms of sort of waiting time benefit for the passenger? If the agency actually has a holding policy that prevents a bus from departing late, more than 5 minutes late, more than 3 minutes late, more than 1 minute late, from a stop in the middle of the route with people inside of it, what happens as you move to tighter windows?
The driver will be less lenient in kind of holding the bus for people running after it.
Especially if you're, right, tighter windows on the early side, more hold-in.
They're like, sorry, we gotta go.
Yeah, yes. So how do you make the bus not be late? What's the strategy for that?
You schedule in more.
You don't schedule for median, right? You schedule for a higher percentile.
Yeah.
So now it's easy, piece of cake. You like schedule it for 80 percentile. Only 20% of the time will you be okay. But what happens? That means that 80% of the time you're arriving early, so you have to hold. So as you make that window tighter, it means that you're probably going to be setting your percentile higher. And it means that you'll be holding more often and slowing service down. And holding is very frustrating for passengers. So you shouldn't hold always and for a long time. Okay, so. And in general, I guess one other comment is like any kind of window, especially on the later side, the benefits of going from 5 to 3 to 1 minutes are going to be marginal in terms of waiting, and they can be substantial in terms of how often you'll have to hold it and how slow the service will be.
I'm sorry, why is holding more often
If you have a tighter window, so
And then you won't be holding.
so if you have a tighter window, if your vehicle must depart between 0 minutes early and 1 minute late, it's a very tight window, right? So how can you guarantee that that vehicle departs that stop in that window? You have to schedule it such that it almost always arrives, right? You have to allow a lot of time on the schedule, so that it almost always it can arrive and it's not arriving 1 minute late.
It's revenue time.
Oh,
Right?
so you're
So you control the late side by scheduling more time,
okay.
right?
People
And then what happens on the early side?
Okay.
On the early side, if you arrive early, you
just sit there.
You have to sit there. Okay, so in long headway service, or low frequency service, there's little interaction between successive vehicles, so bunching is not a normal thing. So we'll talk about bunching in the context of high frequency service. And then of course, real-time information is changing this. So now you have an app, and your app, as you're doing your breakfast, the phone vibrates and says, here's the time, here's my predicted time. So you rush, right? Maybe you'll skip something on breakfast, or I don't know. So that is very poorly understood from a research standpoint. We don't really know how exactly that happens, what percentage of people are actually changing when they would arrive based on the app. And we don't really know what the implications are, because you can't just say, imagine if everybody had an app and everybody used the app, okay? So, and you're running 20-minute headway service. Now you say, well, everybody is going to show up to time the arrival of the stop, right? So let's not worry at all about reliability. It doesn't matter when vehicles come, because people know and they time their arrivals. So now I can speed up service. But there is some sense of convenience of knowing that it runs every 20 minutes. The availability of service every 20 minutes is a factor that wouldn't be considered if you did that, right? So in some way, it is still important, even if people can time their arrival at stops, to keep service as scheduled when it's long headway. And we don't really, how do you measure that? How do you quantify that convenience, that coverage? All questions for researchers.
So is there like for this time window, is there like a defined threshold to define what something that is like very tight time frame, like medium, long, and tight time frame for this? And when does it matter? Because obviously tight is different in the mornings when you have the AM peaks, or in the afternoons when you have the PM peaks, and in the midday, for example.
That decision is sort of up to the agency, right?
It's up to the agency.
Yeah, and usually there's a trade-off where you want to set a goal that is attainable, and you don't want to be reporting 30% reliability. So it's a bar that moves according to the abilities of the agency, usually. That's what happens in practice. Okay, if there are no more questions on low-frequency service, let's move to high-frequency service. A little more interesting. Do you have a question?
Yeah, what's the cutoff here between high frequency and low frequency?
Good question. So what do you think?
Depends on which country you're in.
That is a good point. He said depends which country you're in. That's a very legitimate observation.
America, not America.
So it's not just U.S. and non-U.S. It's much. So
It's also
what
urban, rural.
here in the U.S., here in Boston, what would you consider to be high-frequency service?
Up to 10-minute headways.
10 minutes?
Up to 10. Yeah, certainly not more than that.
If it's
Even say
if it's
8
12 minutes, do you look at the schedule?
Yes.
Okay. All right.
Two divides it as 15 and fudges some of it up to 16 and 17.
So yeah, some agencies say 15. In London, I think it's 12. That's the cutoff. Now, if you go to Chile and you say that you're running 10 minutes, they think of that as long headway service, very long, because they have buses that run every minute. So that's high frequency, and 7 minutes is long frequency. Low frequency. So that's a distinction, at least from an operations standpoint, that people make differently in every country. But in terms of waiting time strategy, I think it still holds that it's somewhere between 10 and 15. Maybe between 8 and 15. We don't know. Obviously, there's a continuum, right? Some people, it's not like everybody switches at exactly some threshold. It depends on the person and what technology they have and what service they're taking. Between those 8 and 15 minutes, or even 12 minutes, there's going to be a transition from one strategy to the other. And you know that when you're sort of well in the high frequency zone, your models of random or at least independent arrivals of passengers at stops hold. Whereas when you have, as you move towards 15 longer, they stop holding, and you shouldn't be measuring waiting time like this.
I mean, I was asking that because even with 10 minutes, which is considered high frequency,
Yeah.
I still want to, sort of schedule myself for when I'm going to get to the bus stop. I'm just like, oh, let me just walk to the bus stop and I'll wait 9
So
minutes.
for 10 minutes, do you actually consult the schedule?
Well, I consult the app.
Well, 10 minutes, half the time.
But do you
it's
plan
less
to
than 10
take the
minutes.
9:10 train, or you see there's a distinction? Like the day before, I'm going to take the 9:10.
If they were running clock-based, consistent 10-minute headways,
Then you would
yes,
show up.
then I would.
Yeah.
But they're not. It's
So
like,
that's
who
10
knows what.
for you. 10 is like right there on the fence between the two. It seems
Okay.
more on the scheduled side, on the high frequency side, perhaps.
Yeah.
Okay, so but let's say that it's 5 minutes. So now we're clear of that vague area. So now you're in a zone where most people will time their arrivals at stops. Will not time their arrivals at stops. They will show up when convenient, and they expect to wait about half the headway. You know that if the headways are variable, you're going to have that waiting time increasing. So there's going to be a reliability buffer time calculation that you can do, and it's going to be the coefficient variation of headway will sort of affect. That's the factor that sort of increases the expected waiting time. Right. So punctuality is not as critical for the passengers, right? They don't really care if every train is 5 minutes late, as long as they come every 5 minutes. It doesn't really matter that they're all 5 minutes late. So really what matters for a passenger is bunching and long gaps. We've talked about that before. We know that in high frequency service there is a lot of vehicle interaction. We can maybe review it quickly. Think of this as a bus route. And here's a vehicle. Each of these are vehicles. So, and there's a random arrival process. So passengers are arriving sort of randomly at the different stops. So, what happens when vehicles are not evenly spaced in time, not in space? So, what happens when they're not evenly spaced?
The one that's close to the next one picks up less.
Okay,
And then the one-
so this vehicle
Yeah.
has a smaller gap ahead of it, right? And therefore, because people are arriving at some rate, in that time, for that rate, fewer passengers will be taking this bus. And that means that dwell times are shorter, vehicle catches up.
Yeah.
So now you have a bunch, right? Eventually this vehicle will catch up to this one. If this vehicle, the one ahead of it, has a long headway ahead of it, the opposite happens, right? More people than average arrive, and then that vehicle has many more people in it, the loads increase, it slows down. So those two effects work together to create bunching. We've talked about that. And with bunching, the counterpart is long gaps, right? You usually have a bunch and then a long gap, or a long gap preceding a bunch. So you'll hear passengers complaining, I've been waiting 15 minutes and now 3 buses arrive, right? As if that were ironic, but that's actually exactly why it happens.
So what's the best strategy to deal with bunching?
We'll talk about many of them.
Okay.
Yeah. Okay, so one observation is that some high-frequency routes have branches, so they're only high frequency in the trunk, and the branches, the individual branches, are actually long headway. And there you have to run scheduled service on the branches, and then you have to, I guess, try to run scheduled service on the trunk. There might be some hybrid strategies, but that's still the subject of research. And of course, schedule control is much easier than headway control. You can do it without technology, right? You can print the schedule and the driver can have the schedule in the vehicle. And you could tell drivers don't leave early, and if they follow instructions, they won't leave early. So if you want to control headways and you want to keep the vehicles evenly spaced, now you need all this technology infrastructure to detect where vehicles are, to predict the running times between them, and to communicate instructions to those vehicles so that the headways can be adjusted. Here's our reliability buffer time. So let's talk about how to actually calculate it in a high frequency closed fare system. So think of the London Tube, right? You tap in the station and then you tap out when you leave. So you can measure the probability distribution of travel time or journey time from tap-in time to tap-out time. And we define the reliability buffer time as the difference between the 95th percentile and the 50th percentile of that journey time. So again, if this distribution were much narrower, then people would not have to budget that difference in their, as they plan to make that trip, to arrive at a certain time at work or school. Okay, so something interesting about this is that London has somewhat recently started refunding fares if people's journeys exceed sort of 30 minutes of the expected. So they're not doing it by percentile, but they here's an application in fare policy, which is not the most obvious one. But you can certainly measure this reliability buffer time. Yes, question?
You know how much that costs us?
No. I don't think much. Well, it is a lot in total, but
Order of magnitude?
I don't remember what percent of passengers have that. I think the percent is quite low, except if there's a big disruption, it might be high. But because of the sheer size of the network, I'm sure it adds up to, yeah.
It's a good marketing strategy.
Yeah.
Builds confidence.
London, they don't talk so much about passengers, they talk more about customers, and they want to have customer service, and so they like to have that internal mentality.
Well, how do they know like someone was dwelling in a station at the transportation?
So because they can look at other people doing that same trip. Right? So if somebody wants to hang out, they're not going to get a free trip just because they wanted to.
It's interesting in the Delhi Metro to prevent crowding. If you spend too much time in the system, they actually give you a penalty when you tap out. And so some of the journeys are so long, people actually have to rush to get out, or else they mess up. their
Not
time.
very good reliability. We can add that to the list. Yeah.
How do they determine the standard or expected journey time, or is it median?
They look at this, so they measure this, and I'll show you the next slide. Before we move on to the next slide, any other questions on this one? I saw several hands raised, so, okay. So they look at good days and bad days, to answer your question. So they pick some baseline of days that have no major disruptions, the service is running well, it's the demand that they expect, and then they'll measure reliability buffer time on those days. So that is an amount that they say is sort of inherent to the operation, and not much under their control unless they invest in better signaling systems or things like this, right? Anything in excess of that, if you look at now all days together, will be something that they could have avoided. That's the idea. This distinction between the baseline buffer time and the excess buffer time. So if that excess buffer time exceeds some amount, you can then say, well, we had a problem. Passengers were taking much longer than we scheduled for, or that we thought they could take, and therefore let's refund the fare because it was bad service.
This is for any OD pair on the Victoria line?
This, yes, northbound. You mean this graph? Yeah, so northbound, southbound, yeah. Yeah. And the thesis, the reference is right here, David Lehman, 2009, so you can check it out in the library if you're interested. Okay, so what happens when it's low frequency? Now, people are not arriving necessarily sort of randomly or independent. Now, they might actually be scheduling their arrival to meet particular training, but of course, trains may not be running on schedule. So you have the space-time diagram here, time on the horizontal and space, or the stations on the vertical. And you see that there is some degree of variability in timing, and if these vehicles were on time, maybe they would be more evenly spaced. So we have taps. Here there's a touch-in at 8 o'clock. And so what we do is that we look at what's the next train, right? When does that tap in aboard, and that's sort of how much they waited. You're comparing to the scheduled departure, which is in this case 8:06, right? So because the train, I don't know if I'm explaining this clearly. So you can match the tap-in time to the closest scheduled departure that follows that tap-in, right? And that's the train that the person intends to board. And that's how much the person intends. The difference between those two times is the amount of time that the person intends to wait or expects to wait. Any waiting time beyond that is excess waiting time, okay? And then you can do the same for the in-vehicle time and sort of add the two components up, and that's how you get reliability buffer time. So you're now considering that the waiting strategy is different. And here's the reference, 2010, another thesis. For bus, there's another challenge. So now, well, there's two challenges. The first one is we need to distinguish between the performance of the contractor, if it's a private operator, and you're paying that company, that bus company, to run service for you, and the performance as the passenger sees it. So, as it says in the bottom, if service is unreliable, the passenger doesn't care why it's unreliable, but the operator needs to know if it's the fault of the operator or if it was an external reason that was not under the control of the operator. Why? Why is that important? Henry.
If there is traffic, then there could likely be traffic downstream as well. And will continue to be on the line for the remainder of the trip.
Okay, but you're thinking of a specific trip. I'm thinking more generally. So why would the agency want to distinguish between bad performance that can be assigned or sort of blamed on the operator versus bad performance that is exogenous?
Because if the bad service is due to some act of God in the agency, maybe you can't hold the contractor accountable. But if the contracted service provider does something wrong, then there can be some kind of punishment.
Okay, yes. And in this case, a punishment under a contract might be a penalty, right? So they might withhold some, if there's a performance bonus, maybe the operator does not get that bonus. And there might be actually provision for a penalty, for a discount on the payment. Right, so, and it doesn't have to be an act of God, right? It can be normal traffic. And the sort of the reliability, the variability in travel times that is expected because of traffic that is not under the control of the operator. But what if the operator is not maintaining his buses and some vehicles have to be pulled out of service? So that operator drops trips and now performance is not as good. That is very clearly the fault of the operator, and you want to penalize the operator. Okay, so that's one challenge. So you have to measure reliability, but you can't. Now you have to assign its sources. Now you have to calculate the sources of those and sort of assign cost codes to these, to whatever you measure. And there might be a mix. The other challenge is that typically buses are only tap on and not tap off. So you have to, journey time includes the in-vehicle portion. So now you have to figure out where this person alights to figure out the in-vehicle component. And waiting time is another portion of this, and the passenger doesn't tap in until they have finished waiting. So you have to go back and calculate how long did they wait. So those are two minor challenges. Here's a strategy. For destinations, we have ODX, right? So we can look at their next tap in. We can do trip chaining, as we discussed previously, and infer the destination for that person, okay? And for some people that will fail, but we can scale up in probability. We can say, well, if this person didn't have a next tap, let's look at the distribution of passengers who do have a next tap, and let's assume that these other people are have destinations that are in proportion, it's distributed in the same way as people who do have destinations inferred. And then from AVL, we can sort of do the same trick that we did for rail. We can assume that there's some process by which passengers arrive at stops. So if it's high frequency bus service, we say it's some arrival rate, right? If it's low frequency service, we say they arrive on time to match the schedule. And then we can compare that with actual vehicle times. So if we have an assumption about when that passenger arrived, then we can calculate the difference and measure the waiting time. So it's more stochastic because you don't know exactly when this person arrived, but in probability, you know that in aggregate across all passengers, any one person arrived between this bus and that bus. Yeah, questions about this process for measuring journey time reliability? Comments?
I just, one thing I find funny about waiting time is like with the bus, they're like, oh,
Yeah.
With the scheduled bus service, the person only waits 1 minute, that's great. But I mean, if I'm waiting at my desk for, 8 minutes, I actually was,
So that goes back to the discussion about apps that we had just a few minutes ago, that you can't just say that because there are apps, then we can just run service unreliably if it's on headway.
Yeah.
Because so if it's high frequency, you probably won't care, you'll just still go. Or you'll be timing it, but you would have arrived randomly anyway to some extent. I.e., your intention to begin the trip is random, or at least independent of the schedule. But if it's long headway service, then yes, you maybe stay at your desk or get a cup of coffee, but you're still inconvenienced,
Right.
and so there's a penalty for it.
Right.
And we need to figure out how to measure it. And one way is to assume that people still arrive or want to arrive on time. And that's what we've been doing because that's what we used to do. And it kind of works, but it's slightly different. Yeah.
So how do you use the stochastic process to estimate wait time?
Yeah, so let's another timeline. So in this case, it's a timeline, not a spaceline. So let's say that there's a tap at that time, and the buses are arriving here, here, here. The tap has to be when the bus arrives, or very close to it, right? Because the person is tapping into the bus. So what you know for this person, assuming that this bus isn't full, is that that person arrived as late as that exactly when that vehicle arrived, and as early as this vehicle. So you know that the arrival time of that person and the time at which they began waiting is a stochastic variable with a uniform distribution on that range. And you know the mean of that distribution is half the headway, right? So if the bus arrivals are high frequency and the person is arriving randomly, then this is certainly true. If it's long headway service, then you have to then consider what the scheduled times were, right? So now you have to do a process similar to what we did for rail, where let me just draw it here. So if this bus was meant to arrive here, then maybe you say, well, this person must have been wanting to get on that bus, and so you make them wait some extra time. And then if this bus was scheduled to depart here, then you know that bus is early. So that means that some of the people that end up tapping here were probably trying to get on this bus, and they missed it. Because they arrived between this and this time, between the actual and the departed time.
So how did that?
And so those are the people who suffer the most, right? And that's more difficult to calculate. You might have to assume some proportion of the people you see here. You could compare to the typical load and see if there's an excess, and assume that excess would have been on the previous bus if that bus had departed on time. So you have to use more assumptions. Okay, so we understand how to measure reliability for rail, tap in, tap out, long headway, short headway, and for bus. So strategies. So the question Eli had earlier was, what do we do about it, right? Now we measure it, so if you can measure something, you do something about it, what can we do about it? So two kinds of things. We can use preventive strategies and corrective strategies. Preventive strategies are aimed at maintaining normal service and having sort of robust operations plan that can handle unreliability without having a domino effect where everything cascades into unreliability, and that it reduces the probability that problems occur. Corrective strategies are you're monitoring the system, you see unreliability, and you do something to the system at that time to fix it, to make it more reliable, and to minimize impacts on passengers. So examples of preventive strategies are having a reserve fleet of drivers and vehicles. If a driver is sick, you have another driver, and you send that driver. The vehicle is not operating, you have another vehicle. Having exclusive bus lanes. So if you have great separation, you get rid of some of the unreliability that comes from traffic, right? Traffic signal priority, that should be transit signal priority. We talked about that in our previous lecture. There are route design strategies. So we've seen that longer routes are more reliable because they have more time between recovery time, between layovers essentially, and they have less stops, fewer stops. So There's less of a dwell time unreliability effect. You can make schedules that have a good amount of recovery at the end. So you look at the percentiles and you make sure that you're not picking the average to calculate your cycle times. And you set the timing points at good percentiles. Maybe it's the median, maybe it's the 40th percentile. And of course, hiring supervisors to make sure that your people are showing up and they're leaving on time rather than whenever they want, etc. So, it's schedules. So, two critical decisions. The cycle time, we know about that. We know that it impacts cost and the reliability of departure time of the terminal. And you're very familiar with that, I think, by now. So I don't have to spend much time discussing it. Timing points is another. So you can, in the middle of a bus route, have timing points. So we know that there might be a terminal here and a terminal here. And that whenever a bus sort of arrives at the end to B, they then have a layover to catch up, right? We know that from assignment 1 even. But you can actually add points in the middle where buses are also not allowed to leave early. And so if you schedule the times of these in some way, then buses might hold more or hold less, and they will depart those points on time. Where should you put those timing points, if at all?
Major transfers.
Okay, so one idea is that if there's a big train station here, or another bus line that also runs, especially for low frequency service, and people want to connect, they need to transfer it and they want to connect. You might actually have a timing point for both routes there, so that the vehicles meet and people can switch vehicles. So that's one idea. What else? Lee?
Maybe like after a high variability section, like after the traffic.
Okay, so you have maybe this lane has a lot of traffic and it's causing a lot of unreliability. So you want to take care of it there instead of letting it cascade into more variable headways, for example. What else?
High demand stations.
High demand stations, okay. So what about demand? Demand is important, but what exactly?
I mean, if the bus is reliable at that station, then the passengers would.
But do you mean, for example, a lot of people getting off from this bus to take that station, or to enter that train station, or?
People are getting onto the bus at that station.
Okay, so right upstream of sections where there are many boardings. That's a very important thing, because that's where most people benefit, right? And what else? What else about passengers? Where would you not want to do this? All right.
When the bus is full.
When the bus is full. So if your load profile looks, I don't know, a lot of people get on here, and they're mostly not getting off, and they sort of come down like that. Do you want timing points on that bus route? You don't. You don't want timing points because most people are getting on here, and they don't want to be held here and here, right? And very few people might be boarding in this section. So if you hold at timing points, you're going to benefit few passengers and penalize by longer and more frustrating vehicle rides many passengers. So what if there's a big transfer station here and a lot of people transfer, and then here there's another station and a lot of people get on. So this is a good place to have a timing point, right? Right before a lot of people board. And when you don't have many people on the bus, the flow profile is low.
Ensure good reliability before that date.
Exactly. So you want to sort of maximize the segment of the population that will benefit from the strategy and minimize the segment of the population that will be hurt by the strategy, i.e. people in the bus. Okay? So that's a word about number and location of timing points. And then the schedule at each timing point. What should you set the percentile at? Should these be the median? Should they be 80 percentile? Should they be 30 percentile?
80th, I mean 80th realm.
So what happens if you, how many vehicles will have to be held? What percent of vehicles will have to be held if you set it to 80th percentile?
Oh, 80%.
80%. Okay, so 80% of vehicles will be sort of getting here and waiting. That may be acceptable if again very few people are here and a lot of people are boarding. What if it's more of a mix? Then you want to bring that down, right? You dial it down. So some people say set the half cycle to somewhere between 90 and 95. We've done that, and then set timing points to 65. I actually prefer that the timing points are below 50. Because then you can advertise to your passengers. You're essentially lying to people and saying, you're motivating people to arrive earlier than most often the vehicle arrives, right? So their probability of arriving and missing a vehicle that departed early is lower. Because you're telling them, expect an early departure, essentially. Except you don't call it early. You say that's when it's scheduled to arrive. Okay? So essentially you can control this by scheduling a certain way, and then on the other side by controlling it.
But the pushback when people are like, oh, the bus is always running late. It's always
Yeah.
a couple minutes late.
But yeah, so it affects, there's a balance, right? I'm not saying schedule at 10th percentile. So
90%.
yeah, but I think a little below 50 is a good strategy. Because then you would minimize holding. You would only hold vehicles that are really early, essentially. And holding is frustrating. You don't want to be doing it all the time. So by scheduling at a lower percentile, you don't hold as often, and you don't hold for as long times. All right. You have to be careful when you do this, when you have timing points, because then your AVL data will come in, right? And you're gonna say, what's the running time? Well, if people are following your instructions, the minimum running time will be whatever your timing points are. So maybe your distribution would look like this, but because you have timing points, you've chopped off the early portion. And now it looks more like this. And now your 95th percentile is more to the right than it used to be. Maybe. Maybe not. Maybe it stays where it is. But you have to be careful with this. Your average will certainly move to the right. So just be careful about that. One strategy is to measure distinguish holding from running, but that's a little difficult with AVL sometimes. Another strategy is to run a month without timing points. Essentially instruct your drivers not to use timing points and collect data for a month and then use that for planning. So just things we can do. Okay, now corrective strategies. So obviously supervision, having supervisors, having an operations control practice is important. There's different strategies. This is one of my favorite topics in transit. So holding, you can do holding to schedule or to headway. So what is holding to schedule? That's the simple one, right? We've mentioned it a dozen times, and even on this lecture. You don't allow a vehicle to depart early from a timing point or from a terminal. So if a vehicle arrives a minute early at a timing point, you instruct that driver not to hold 1 minute. Even though that bus is able to move on, that bus hold for 1 minute. TSP we talked about. What's deadheading?
Just moving a bus from one place to another that's not a revenue.
Okay. So let's say let's say that you have buses here, and this is your terminal. And there's a bus that you are about to depart, and your headway, the scheduled headway, is more like this. So you were supposed to have a bus here, but you didn't. Something happened, and the bus wasn't there. So, and now you have 2 buses there instead of 1. Maybe there was bunching on the way back, and the bunch arrived late, as it usually happens. So one strategy that you can use is to take the first one and instruct a deadhead to somewhere around here. Okay, so this bus would run without a head sign on, not allowing anybody to board, and that's why it's called a deadhead, to this stop. And then this bus departs immediately, but in revenue service. So if that deadhead can happen quickly, maybe not even following the streets of the bus, maybe there's a faster way, and you inject it downstream, you can speed things up, you can balance the headways. What's expressing?
Skipping stops.
That's one way of doing expressing. Expressing can be done from the terminal, right? So the distinction between expressing and deadheading is that expressing is done with people inside. So in this case, you could have allowed people to board at the terminal and then said, we're going to run express. You tell people who are boarding, we're going to run express. So if you're getting off anywhere between here and here, don't board. And the vehicle then skips stops, but with people inside. So I don't think I need to do a drawing for this one. Expressing can also be done halfway through. So if you have this situation, then you could say these people might have boarded not knowing that this bus was going to be expressed, but something happened. Maybe this driver was slow, maybe there was some traffic accident and there are delays. So you can then announce this bus is being expressed or this train is being expressed, and we're going to skip the following 3 stops and arrive somewhere. So if you're getting off before the express, you have to decide, are you going to stay and then walk back? Are you going to stay and then take transit the opposite way? Or are you going to get off right now and wait for the next vehicle? So it's a higher penalty for passengers. Okay? What about short term? We've talked about all of these, but in the context of planning, and now we're using them for real-time control. So this is deadheading. Right, and then, so short term. Here's the situation. You have this doesn't happen often, but it does happen.
For the passengers.
You have a bunch in one direction and a very long gap in the other direction. And what happens with bunching? The bus behind is usually not very full, right? So you stop these buses in the same stop, and you tell the people here to move to the bus ahead. Just get off the bus, we're going to short term, we're going to terminate the trip here, and those people have to transfer to the next bus. If you don't allow this to happen, then it's really onerous for passengers, because they have to get off and wait for the next one, right? So it's better if you coordinate it this way. And then this bus gets sent here and begins operating in the opposite direction. Lee.
How much of this is done automatically versus like a person looking at this?
I don't know of any case where this is done automatically. There have been researchers here at MIT and elsewhere, including me, who have tried to sort of write algorithms that detect these opportunities, but I don't know of any real implementation. London Buses does this, or at least they used to. I think they still do. But they really try to coordinate this. They very rarely curtail trips without coordinating in a bunch, because then people have to wait for the next one.
BART trains do this as well.
Sorry?
The train systems on BART.
Yeah, yes. So in trains it's more common, but it's usually a person in a control center taking determining that they want to do this.
What's stopping them from implementing more algorithms? Is it that algorithms are not good enough, or?
So that's part of it, and then yeah, I think I would say that's part of it. The other is maybe lack of interest or lack of faith in a computer. Yeah. There's a system in place. It's just, it's hard.
But there are two elements to this problem. One is that you have to detect a problem in one direction, and the other thing is that you have to detect an opportunity in the other direction.
So this doesn't happen very often.
There are two parts here that are completely independent from each other.
They're not independent though. If the route is long, you actually have, even though in a short route in any given segment the probability of this happening is low. If you have a long route, it's much higher. It's the point you brought up with Dr. Firth's, Professor Firth's lecture. You said, oh, the chances of a bus benefiting from this are very small. And then you said, well, what if it's a long route and there are 20 signals? Same thing applies here. You might have a long route with many windows, and the chances that there's one window at any given time in the rush hour is actually pretty high.
And then the other thing is, as the controller, suppose I'm the controller, I have the algorithm, and my computer starts beeping and gets all excited. I have to respond quickly to this because that opportunity will pass.
And getting back to algorithms and anticipation, what's sort of neat about algorithms is that you can try to predict that this will happen rather than waiting until it happens to react. And if you can do that early enough, you might actually instruct the bus that is departing the terminal to short turn later on. And if you do that, then you can set the head sign on the bus to the short version, and people who are boarding it are going to know that it's going to be short turn, so you don't have to coordinate with the bus next to it. You don't have to have a bunch, in other words. So you can then minimize the problem to finding a long gap here and predicting when that gap will meet the new bus that is being dispatched.
But what do you tell?
You need algorithms for that. It's very difficult to do.
What do you tell the passengers? Do you tell the passengers, listen, guys, this bus might get short-term, just so you know.
No, you change the head sign and you say this bus is running to.
Okay, but that's
it's running to Central Square instead of Harvard. Yeah.
Because wouldn't you know that this is going to happen during commute hours? Like the red line I suppose for trains, the red line is so long, but if you know your OEs are mainly in the downtown area, wouldn't you know beforehand that you want to just have higher frequency on this one branch?
That would be a service planning short turning strategy, not a real time control strategy. So we make the distinction. Both are short turning, but this is something that you decide in real time to bring the service that you're delivering more close to what you plan to deliver, which is different from a strategy in service planning where you identify. When we talked about high riders or corridor strategies, there might be a core of your route that has higher demand, and you have short turns to have frequency higher at that point. Very different reasons and horizons for planning and all sorts of things. Use of reserved vehicles. This happens more with rail than bus. You could have it with bus too, though. I know that in South America they do it with bus. So you have some buses stationed somewhere in the city near key routes, and they're just waiting there for an opportunity. And right. So then someone in a control center sees a long gap, and they call that bus and say, "There's a big long gap there. Rush, go into that corridor and start operating route X." So they can inject the vehicle, and you can do that with rail too if you have pocket tracks. So you might have pocket tracks somewhere and sort of insert a train. Ari knows something about that. So mostly if you do holding, holding is the best strategy for sort of keeping service on track. You don't usually want to do the more aggressive strategies because they hurt passengers and they require much more coordination effort. But if you have a major disruption, sometimes you need them. Holding by itself won't cut it. Holding can be done in a bunch of different ways. You can hold to schedule adherence, we've spoken about that. For headway, we've kind of brushed it off and said headway adherence. Well, there's actually a lot of ways you can do that. So one of them is to look at the schedule and realize that the time between scheduled trips is 5 minutes. So now instead of actually trying to stick to the actual times, you want to stick to a separation of 5 minutes between vehicles because that's the time that was scheduled. So that would be scheduled headway adherence. The next, and these are in order of sophistication. So the next one is threshold headway adherence. So if you think about it, there's no reason why the scheduled difference between departure times is the best threshold that you should use for holding. There might be one that is a minute less or a minute higher that results in better performance. Why not? Why should the schedule? What physical reason is there for the scheduled time being the best one? There isn't any. So if you optimize the threshold, you can get better performance. And usually the optimal threshold is shorter than the schedule. So you hold less often. The problem with headway adherence is that you hold too much, essentially. So then there's headway regularity. Don't worry about the schedule at all, or about any predetermined headway. You have a separation between vehicles, and I know that if I have vehicles, I want my vehicles spaced this way, but instead I have this situation. So I want this vehicle to hold until it is here, right? Or rather, that vehicle, what will really happen is this vehicle will stay there, you'll ask it to stay there, and you want this vehicle to move on, and this vehicle to move on to these positions, and now they're even, and then you let that vehicle go at that point. So that's even headway holding.
That seems pretty easy to implement. How often is that?
Now it is, it used to be very hard. So how would you implement target headway holding without technology?
Right, we're saying now we have.
No, but how would you? You can do it.
You need a supervisor.
You need a supervisor.
You have like a
so in London, there was actually a time when you didn't need a supervisor because you had the driver getting off the bus and hitting a button on a post. It starts a timer, and then the driver leaves. The next bus comes along, and it sees the time. So it knows like, okay, this is when I have to leave. And then, so you can do that even without wireless communication. Even headway, you can't do that. You need communication. Somebody needs to know the vehicle before, the vehicle after, that needs to be communicated. So it's a much more sort of recent strategy in terms of.
Oh, so in this strategy, you're not necessarily trying to maintain a certain headway.
No certain headway. It's optimal and it emerges from the system.
Okay.
Yeah.
Okay.
And there's actually, if we want to split hairs, there's different kinds of ways of doing even headway, and let's not get into it. Then the most sort of sophisticated class is optimization, and there's something called rolling horizon optimization. So what happens there is that you use a simulation model essentially to predict how the system would evolve if your holding times were a certain configuration. And you can test a bunch of different headway holding configurations and pick the one that's best at a given time based on those forecasts. In other words, pick the holding time that maximizes performance across forecasts. And so what's neat about these is that they can trade off waiting time and in-vehicle time. When you hold, the people inside the vehicle are waiting more. The winners of this strategy are people who would miss that bus and have to wait for the following bus that has a long headway ahead of it, right? So by evening out the headways, you make everybody wait about the same, and that minimizes average waiting time and average crowding, etc. So an optimization strategy can predict or keep track of how many people are inside vehicles, and it can know, well, I know this is the penalty, I know this is the benefit, let's trade these off and let's hold the optimal amount of time such that the total time is minimized. And you can multiply by factors that take into account the disutility of waiting being higher than the disutility of being inside the vehicle. So what that does is that it reduces excessive holding. So if you know that you have a full vehicle, you don't hold it, even if it's very close to the next one. Why would you hold a vehicle that is full? Even if it's this one right here, bunched to the next one. You don't want to hold it. What if the vehicle isn't full, but it will be full 5 stops ahead? Because the demand is very high for some reason, and you know that, then an optimization algorithm will see that because it's predicting for the next hour. So it'll be able to pick a strategy that improves performance. One challenge is drivers. If you hold too much, then drivers might be 20 minutes late for their shift, for their meal break. What do you do about that? That's still a challenge. And that's a challenge throughout. But there's opportunity with optimization algorithms to insert constraints that take those into account so that your holding policy is something that you can implement.
Seems like another constraint would be the speed of the algorithm. Like if it's taking
Yes.
45 minutes to come up with this
Indeed.
great solution,
Yeah.
it's too late.
So this problem is NP hard, and if you crunched all the possibilities, you would never finish.
Right.
So you need a very good algorithm to sort of find something fast. So there's 2 different ways of doing rolling horizon optimization. Your one way is to have constant running times in demand within the prediction horizon. So imagine this blue window being this is the time right now, and you're predicting over the next, say, hour, and that's the blue window. What is actually happening is that your running times are going up slowly, gradually. Your demand is going up slowly, gradually, because you're in the PM peak. If you are using static input, you have to say what the running time is for the whole horizon, right? So what you might do is break up the day into periods, and if you start at this time, any time before this, you set some average, and then once you cross that threshold, you set a different average, but then you miss out on some information, right? So I worked on a model that actually takes in dynamic inputs to sort of figure out, to consider these transitions, essentially. And the way it works is you have these dynamic functions of running times on demand. You can see the current system state. You send that to a model. The model passes on those inputs and some holding time configuration to a performance model, which essentially forecasts what the system would do, how the vehicle would move, where passengers would board, all those things. And then that gets sent to a cost model, which says how much are people waiting, how much are people in vehicles. Let's add those up and figure out what the average is. And then that gets sent back to the optimization model, and the optimization model says, what if we, instead of doing that, let's turn this knob and increase that holding time and decrease this one, go again. So it can do that on a loop, and essentially until it finds optimal times. The objective function is the average time in the system. So WV is like extra time in the vehicle. So it's the time that a person spends at a stop in the vehicle, not moving because the vehicle is being held, right? So you're adding time to that person. And then WS is waiting time at the stop. And we can multiply by some factor because we know that waiting time is more onerous. There's a bunch of constraints. I'll skip the differences between static and dynamic. Essentially, it's that running times and demand can be functions of time now. Here's what happens. So here we test 4 different strategies. The first one here, TH, is threshold holding. EH is even headway holding. OS is optimization with static inputs, and OD is optimization with dynamic inputs. And then we tested, if we look at the bottom sort of 2 sets of 4, these are cases where both the demand and the running times are dynamic, so they're both transient. And we tested a case of low crowding and a case of high crowding. So what we see is that in all cases of low crowding, by the way, the bottom sort of 2/3 sets of runs are cases where maybe running times are dynamic, but demand isn't, or demand is dynamic and running times aren't. So if you look at all the cases of low crowding, the white ones here, there's very little difference in performance. So it means that you don't really need the most sophisticated strategy. And the benefit of a very sophisticated optimization strategy with dynamic inputs is not really going to bring you a lot of benefit. If you look at the high crowding case, what you see is that so there is a pretty significant benefit of even headway holding over even optimized threshold holding. But moving to the model with optimization doesn't do much for you. if there's a lot of sort of dynamics in the system, essentially. So part of that is because the static inputs hide information about when those vehicles will fill up. And when you insert that information into the system, then the optimizer can see more of what happens and can improve performance. Here, to the left is lower cost and therefore better. Yeah, there's more to parse here, but we're running out of time, so I'm gonna skip a few slides. So you have control problems, routine disturbances, where you do speed adjustments and holding lightly. Then there's short-term disruptions that might last between 5 and 30 minutes. And there you can apply the strategies that we've discussed. And then there's much longer interruptions in service, for which you need to do something major, like bringing out bus service to replace train service. And so only holding short-term and expressing that heading, they're not going to cut it. You have a much bigger problem to deal with. Here's a situation in a rail operation where there's a signal failure, or perhaps there's a suicide attempt and there's a person on the tracks, and you have this train that's standing there and can't move. So the first thing you should do is hold the trains downstream, immediately downstream of the blockage. If you don't do that, they will run around and queue up on the other end, and the people entering these stations are going to wait a long time, right? And those stations are going to fill up. The other thing you should do is these trains that are lined up here should be expressed as soon as the blockage is cleared up, so that you can move those vehicles forward, and the vehicles at the end of the queue can begin normal operation. Okay? Does that make sense? A lot of the very sophisticated models are not used in practice for a number of reasons. Sometimes it's that the models are simplistic. Sometimes it's a sort of a lack of faith in models. Often it has to do with the data in real time about where vehicles are not being that good. So actually detecting where vehicles are could be a major challenge. And you need that information to make a determination of what the optimal strategy is. Recently, our lab did a pilot of a real experiment with a green line holding to headways instead of the schedule. So right now they use paper sheets and they have the schedule, and Josh Fabian, who's a student in the lab, designed an app that has all the train and driver information, and it also calculates the even headway departing time. So that departure time, which would cause an even headway. And for 2 weeks, we had the inspectors of the terminal use that instead of the paper schedule. And what happened, here's a picture of the app. So you have all the trains for the day. There's color coding, so like green is coming up, and you can see that these times are different. So 9:36, there's some extra holding there for the train that had been scheduled at 9:34, so that the headways are even coming out. And here's what happens. The sort of variability decreased by about 40% in some cases if you look at the coefficient of variation, and you only look at trains that were compliant. What really happened overall was a mix of things. There was some non-compliance with the headway times, some insistence in departing on time to the schedule, and then sometimes compliance to the even headway policy. So here's the coefficient of variation. You know what that is? You know that lower is better, and the green line is lower, so it's better. You can calculate the equivalent benefit that you would get by adding trains to service in terms of decreasing waiting time. You can increase frequency by adding new trains. So the decrease in variability of headways was equivalent to adding 1.7 trains, which is money, right? So.
Yeah, but if I'm not mistaken, you correct me if I'm wrong, there is a mechanism in this algorithm that tries to go back gradually to the schedule.
No, I wouldn't characterize it that way. There are constraints to prevent situations where there aren't enough trains to be departed, and there are some constraints on how much holding there can be, etc. Yeah. So yeah, there's an intention not to have too much of a cascading holding effect throughout the day.
Okay.
But it's not so much as a programmed linear trend towards schedule or anything like that.
Because you're going off schedule, does
Slightly.
slightly. So would you ever run into issues with like communicating with the public?
The green line, especially in the peaks, high frequency, not running very reliably anyway, so I don't know anyone that looks at the schedule, maybe very early in the morning, but I don't know, maybe late at night, but I don't know
I've
much.
totally used Greenland schedule, but yes, late at night.
Late at night, yeah, late at night I think it would happen, but I don't think that during the day it would happen. And what happened with this late at night is that the schedule is reliable enough that the even wait times are the scheduled times anyway, so there's no issue there.
So would there be an issue in terms of applying this to like a more robust system?
We learned a lot from this pilot, and I think whoever implements the next real system will have to read Josh's thesis, because there's so much that we learned about compliance, about issues with data. Yes, I recommend reading it. Eli.
Like, can you explain one time how it's determining the headway that it should be?
It's even headway.
It's just maintaining even headway. It's not like optimizing.
No optimization. It's a very simple even headway strategy.
Okay.
Prediction of the time it takes the train to reach the next one. Prediction of the time it takes the trailing train to arrive at the terminal, and then using those to calculate the headways essentially.
Okay.
And then determining the holding time to keep that train in the middle, and then adding some constraints to prevent excessive holding. Also to prevent, like if there was a long gap, you might want to not hold the second one too much. Send those together. So here's something interesting. Here's a space-time graph, time on the horizontal. Green here shows compliance, and red shows non-compliance. So the first thing we see is that when there's a lot of green, those lines are nicely evenly spaced. So that's good, right? That's the lower coefficient of variation. When you see red, you see some bunching later on, and it doesn't happen immediately, and it's slight. Notice how slight the deviations can be, but you see the effect of the well-time effect and the bunching happening. The other thing that happens is that they have someone controlling a reservoir. So they have someone stationed there holding trains to keep them evenly spaced, more or less. And which trains are being held? Mostly the ones that are not as green, right? So you've sent a train that might be full of people, and you decided that you somehow need it to depart a little bit earlier than the algorithm said, and then you wait till you're full to then hold 2 minutes. You could have avoided that by having left a little later from the terminal.
Is there another hold at Fenway? Fenway seems to.
No,
Just long.
no, just long dwell times. So that's the end. Sorry for being a few minutes late. If you have questions on holding or real-time control, let me know. Next lecture is on fair policy.